A classical particle is described by its position q naught and momentum p naught. Suppose that this is the initial state of the particle, then Poincare recurrence theorem assures us that the dynamical evolution of q and p will return arbitrarily close to its initial state as long as the system is bounded. However, this will lead to some contradiction when we approach the thermodynamic regime. By considering a free expansion of gas, we can observe that the particles will return arbitrarily close to their initial configuration. This is known as the recurrence paradox since this violates the second law of thermodynamics. This was reconciled from the calculation of Boltzmann and McLennan that the Poincare recurrence time of this system is much larger than the age of the universe. In quantum mechanics, an analog of Poincare recurrence theorem is made by Bocchieri and Lowinger. This is valid for a system with discrete energy eigenvalues. In addition, this theorem holds for closed quantum system. However, it is much more accurate when we describe our system as an open quantum system. This means that we do not disregard the interaction of the quantum system with the environment. One interesting phenomena in open quantum system is decoherence. This can be observed as the vanishing of interferences in a measurement. Decoherence is also considered as a leakage of information into the environment. Now, we may ask if whether decoherence is a reversible or an irreversible phenomena. From the studies of Braun and Zurek, we are motivated to determine the necessary conditions for reversible, quasi-reversible, and irreversible decoherence. In this study, we consider a Hamiltonian that is given in equation 1 where we find the metric of the reduced density matrix. We analyze the behavior of the metric based on the three models of the environment: the homogeneous environment with commensurate parameters omega and g, the homogeneous environment with incommensurate parameters omega and g, and the heterogeneous environment with a uniformly distributed interaction coupling. For commensurate homogeneous environment, the dynamics of the state is reversible since we can see the exact return of the time-evolved state to the initial state. Meanwhile, the incommensurate homogeneous environment shows the dynamics of the central qubit, which is quasi-reversible. And lastly, the heterogeneous environment shows us that an irreversible decoherence is plausible that is within the given timescale of the plot. To know more of these results, I'm inviting you to attend in my thesis defense on 3rd of June. See you!